All right, today we're going to talk about the chain rule for derivatives. The chain rule is going to help us find the derivative of a composition of functions. So before we do that, let's review, just in general, compositions of functions. So I have this lovely function here, f of x equals sine squared of the cosine of x over 2, and we'd like to find f of pi. All right, well, couple of things in here. One thing to realize is sine squared of something means the sine of that thing, cosine of x over 2, all squared, right? That's what it means. Sine squared of means sine of blank squared. All right, so if we want to find f of pi, we're going to go plug a pi in. So I'm just going to rewrite it. I have the sine of the cosine of pi over 2 all squared. When we evaluate a composition of functions, we start on the inside. So I'm going to find the cosine of pi over 2, which we know is 0. So we have the sine of 0 squared. And then we keep going, go back to the inside. The sine of 0 is 0, and 0 squared is 0. All right. Perfect. So just as a reminder, when we evaluate a composition of functions, we start on the inside and we work our way out. All right. So let's start to model some derivatives again. It says using what we already know about the power rule for derivatives, let's just take the derivative of this function here. So we've got y equals the quantity 3x plus 2 squared. So our guess, I'm just going to write this down, our guess is that y prime equals 2 times 3x plus 2 to the first, right? There's our power rule, which if we were to simplify, we get 6x plus 4. I'm going to put a little question mark there. And we'll talk about why there's a question mark there. But, you know, what we can do is to FOIL this, right, before we take the derivative. That way we don't have to worry about it. So if I think of this as 3x plus 2 times 3x plus 2, I get 9x squared plus 6x plus 12x plus 4. So there's my function. And now we're super confident taking this derivative, and I get 18x plus 12. We know this is the derivative. This is what we thought was the derivative. Right? And what's the difference here? Well, the difference here is we're off by a factor of 3, right? I'm going to say our guess is off by a factor of 3. Well, let's think about where that 3 is coming from. When we use the power rule up here, we brought the 2 down in front and subtracted 1 from the exponent. But we never touched this because we haven't yet this year needed to do that. But let's think about it. We're off by a factor of 3. Where do you think that comes from? Well, looks like it's the slope of this function. You could also think of it as the derivative of the inside. I'm going to write that down. The derivative of the inside is 3, isn't it? Okay. So we're thinking we can still make this work. We can still leave this alone, but we're going to need to adjust our answer in the end. So we started with the power rule, but maybe we need to multiply by 3. Okay. We'll write this down formally here in just a minute. All right, so I messed up here because you're not sitting in front of my computer, so I can't show you. I don't actually have this CAS Inspire. A CAS is a computer algebra system. Inspire calculator. I just have it on my computer, and so I can't actually switch and show you that. So I'm going to write down what the derivatives actually are, and then we'll see where those things came from. So if I were to ask a calculator to take the derivative, you cannot ask your regular Inspires, you cannot ask your 84s, they won't do it. But if I were to ask a CAS version of a calculator to take the derivative of the sine of 2x, it would spit out 2 cosine of 2x. Well, let's think about it for a second. The derivative of sine of 2x is cosine of 2x. And the question is, where does that extra 2 come from? Oh, well, It's the derivative of the inside. If I were to ask the calculator to take the derivative of this function, it would spit out 5 over 2 square root of 1 plus 5x. Let's think about why. If I start with 1 plus 5x to the 1/2, the derivative, the power rule, would bring that 1/2 down in front, and we would subtract 1 from the exponent, which if we clean that up, the 2 is in the bottom, the square root is in the bottom. What are we missing? We're missing this extra 5. Where do we think that 5 comes from? It's the derivative of the inside. Okay. So let's write this down and let's practice. Let's talk about first what I've been saying. The chain rule tells us how to take the derivative of a composition of functions when we have one function inside another function. So this does not say f of x times g of x. It says f of g of x. I'm going to go ahead and use my red pen to kind of exaggerate that set of parentheses. So when we evaluate a composition of functions like we did on the first slide, we started on the inside and worked our way out. With derivatives, we actually do the exact opposite. So we start on the outside of those red parentheses and we have f. The derivative of f is called f prime. We leave the inside alone. So the inside is g of x, it stays as g of x. The only thing I did was to take the derivative of f. So f prime of whatever was on the inside. Then the chain rule says you are going to multiply by the derivative of the inside, which we'll call g prime of x. Okay, so again, the chain rule says start on the outside and work your way in. Okay, so let's take a look at some examples. Here we have a function. It is a composition because we've got something inside this power. Okay, so the chain rule says we're going to start on the outside. Here's my parentheses. On the outside of the parentheses is a -5. That's a power, so we're going to start with the power rule. So I bring that power down in front and I subtract 1 from the exponent. The inside stays the same. So we just took care of the exponent. Now we're going to multiply by the derivative of the inside, which is -4. Okay. If we wanted to, I'm not stressing this, but if we wanted to clean this up, I'd have a positive 20 on top and a 1 minus 4x to the 6th on the bottom. Okay. All right, let's take a look at some more examples. All right, so differentiate, take the derivative. Sorry, I'm going to fix my paper here. So just like we would always do, the first thing I'm going to do is rewrite any radicals with fractional exponents. So there's my original. Here's my parentheses. We always start on the outside. Outside of the parentheses is a power, so we will start with the power rule. So I bring the 1/2 down in front, and I subtract 1 from the exponent, right? Don't get wrapped up in, right, just finish the power rule. The inside, 3x squared plus 5x, stays the same. So we just took care of the power. I'm going to cross it off. The chain rule says multiply all of that by the derivative of the inside. Now the inside has 2 terms, so we better make sure we use parentheses, and we'll get 6x plus 5. Okay. Now, if we want to rewrite that, if we want, the 2 goes in the bottom, that square root goes in the bottom, so in the top I have a 6x plus 5. In the bottom I have a 2 and a square root of 3x squared plus 5x. Good. All right, let's take a look at the next one. G of theta equals sine squared of theta. The first thing I'm going to do is write that as the sine of theta squared. Right? That's what that means. It's what we would do if we were going to type this in a calculator. And now we see a function inside another function. So when I go to take the derivative, I start on the outside. Again, the outside is that power, so I bring that 2 down in front, subtract 1 from the exponent, it gives me a 1, I didn't write that down, and I left the inside alone. And then I'm going to multiply by the derivative of sine theta, which is cosine theta. And honestly, there's not much to simplify there. I don't need the parentheses. So I could just write 2 sine theta cosine theta, but it doesn't really change anything. Good. Let's look at this next one. d dx, take the derivative of the cosecant of x over 4. So it's not just the cosecant of x, it's the cosecant of another function. All right, so one thing I might do, this may help us, is to write this as the cosecant of 1/4 x. Whether we do that now or later, I think that will help a lot of us realize, what the derivative of the inside will be. So here's my inside, my 1/4 x, or my x over 4. Outside, or what we're doing to that parenthesis, is taking the cosecant of it. That's on the outside. The derivative of cosecant is negative cosecant cotangent. Notice I just left some blanks there. I'm going to actually come up here and just remind us. The derivative of cosecant x was negative cosecant x times cotangent x. So wherever I had an x, they had an x. So wherever I had a 1/4 x, I'm going to put in a 1/4 x, or x over 4. That's absolutely your call. So I just took care of the cosecant when I wrote negative cosecant blank cotangent blank. The blank stays the same. The chain rule says multiply all of that, which I don't need parentheses or anything, that's all just one term, by the derivative of 1/4 x. Well, the derivative of 1/4 x is 1/4. Certainly we could rearrange that. I would probably put my negative and my 1/4 together all the way out in front, just so I don't lose anything. All right, good. Let's take a look at this one here. Find y prime if y equals 3 over 4x squared plus radical x. Now, honestly, we don't need the chain rule for this. We could use the quotient rule. We could. It's a quotient. You could use the quotient rule. I'll write that down. We could just use the quotient rule, but here's what tells me I shouldn't have to use the quotient rule. My numerator is not a variable, right? It's just a constant, which means when I go to take the derivative of the top, I'll get 0. It's going to wipe something out. So it just almost seems like this quotient rule is too much. So what I'm going to do is I'm just going to rewrite this as 3 times 4x squared plus radical x to the negative first. I'm just going to bring the denominator up to the top and use a negative exponent. Now I'm going to get my red pen out again, because now I see I have a function inside that exponent. So I have an outside, an inside and outside. So when I go to take the derivative, what's outside? Well, a constant. We know the constant's going to stay there. That's the constant multiple rule. It's an exponent. So let's bring that exponent down in front and multiply and subtract 1 from the exponent. I'm going to leave the inside alone. The chain rule says multiply by the derivative of the inside. The inside is 2 terms, so I need to make sure that I leave room for both and use parentheses. The derivative of 4x squared is 8x. The derivative of radical x is 1 over 2 radical x. Honestly, I think that's something at some point we need to have that memorized, right? If you start with x to the 1/2, its derivative is 1/2 x to the negative 1/2, which if you just clean that back, it's 1, or clean it up, it's 1 over 2 radical x. I honestly think that would be something that will save you some time, just a personal preference there. The derivative of the square root of x is 1 over 2 square root of x. That's just me. In terms of cleaning this up, gosh, I don't think there's a whole lot I would want to do with this. I mean, we could. It's not going to look great, but we could have in the numerator, if you want, in the numerator I have -3 times the quantity 8x plus 1 over 2 radical x. And in the denominator I have the quantity squared. Again, it's not great. You don't have to do that. Okay? All right, last one. We've seen this notation before. Find the third derivative of the cosine of 5x when x equals pi over 2. So we want the third derivative. So let's go ahead and write that down. We're going to find the third derivative.
Connie Thomas, stop by the front office, please. Connie Thomas.
Sorry, and plug in x equals pi halves. All right, here we go. I'm going to come down here and write the original y equals the cosine of 5x. And I'm going to grab my red pen again, and there's my parentheses. On the outside of those parentheses, the cosine, we're going to start there. The derivative of cosine is negative sine of 5x, right? The inside stays the same, times 5. There's my chain rule. The derivative of 5x is 5. So you know what I'm going to do? I'm going to put that -5 out in front just to put my constants together. There's my first derivative. All right, let's find the second derivative. Now, the constant multiple rule says the -5 will stay in front. And now I just need to take the derivative of the sine of 5x. Chain rule. The derivative of sine of 5x is cosine of 5x. Multiply by the derivative of the inside to get another 5. So now my second derivative is -25 times the cosine of 5x. Great, now we're ready to take the third derivative. I have a constant being multiplied by my function. The constant multiple rule says the -25 will stay there. And now I just need to multiply by the derivative of the cosine of 5x. Didn't we already do that? We already said what the derivative of the cosine of 5x is. It's negative sine of 5x times another 5. So let's clean that up a little bit. So now I have a negative times a negative. I have a 5 times 25. So I have 125 times the sine of 5x. That's my third derivative. Now I just want to plug in the x equals pi halves. So I have 125 times the sine of 5 times pi halves, or the sine of 5 pi over 2. The sine of 5 pi over 2, well, 5 pi over 2 is really the same as regular 1 pi over 2. So I have 125 times 1, which is 125. So just be very careful with the repeated use of the chain rule. Every time I took the derivative, I multiplied by another 5. Don't lose those.